Today we will talk about Bayes' theorem. Recall that given two sets A and B, these are events inside the sample space S. And if we know that the probability of B is greater than 0, then we can define the conditional probability A given B as the probability of A and B divided by the probability of B. This is the probability that A occurs given that B has already occurred. We can define a partition for a sample space. This is a collection of sets A1 through AN, and it satisfies two important conditions. The first condition is that A1 through AN are mutually exclusive. That is, AI intersect AJ is the empty set for all I not equal to J. Furthermore, we require the set AI through AN to be exhaustive. That is, the union is going to give me the entire sample space. Let B be any event inside the sample space. We're going to use the partition to slice B into disjoint parts. B is going to be the union of B intersect AI, and since the AIs were disjoint, B intersect AIs would be disjoint from each other too. We can visualize this picture as follows. We have partitioned the sample space into 8 parts with the AIs, and the B intersect AIs have been identified. So the green region is the set B. Then we can now use this partition of B into disjoint unions to calculate the probability of B. This is going to be the sum of the probability of B intersect AIs. This equation is called the law of total probability. And since we know from the multiplication principle that B intersect AI equals probability of B given AI times probability of AI, we have that the probability of B has to be the sum of B given AI times the probability of AI, the sum being over all I going from 1 through n. We can visualize this situation as follows. So we have the AIs, the B's coming out from each AI, and the events B intersect AI is identified as follows. We mark out the probabilities across each of the edges. Important thing to notice over here is that given an AI, there are multiple events that could emanate out of them. B is just one of those. Okay. Now, given an event B intersect AI, the probabilities for each of these can be calculated using the multiplication principle as the probability of B given AI times the probability of AI. We can notice that if we take the union along these columns, we will get all of B. And if we take the sum along the probability column, we will get the probability of B. The probability information in the above picture, that is the probabilities of the events AI and the probability of B given AI for I going from 1 through n, are called prior probabilities. The goal is to use these probabilities to calculate what are known as posterior probabilities. Bayes' theorem is going to help us make this precise. So the posterior probabilities are the probabilities of the events corresponding to AJ given B. So we will call these the posterior probabilities. Notice using the multiplication principle, the probability of AJ given B is the probability of AJ intersect B divided by the probability of B. And now we can solve this equation to get the following formula, which is known as Bayes' theorem. Notice that all probabilities on the right-hand side of this equation can be calculated from the tree diagram. Bayes' theorem can feel confusing, so we will spend some time doing a very concrete example. Consider that a city has two types of cabs, blue cabs and green cabs. Let P of B be the proportion of blue cabs in the city. And in this setting, P of G is going to be 1 minus P of B, which is the proportion of green cabs in this city. Suppose there was a hit and run incident involving a cab in the city, and we want to try to calculate the probability of the color of the involved cab. With no additional information available, the probability of the involved cab being a blue cab is going to be exactly the proportion of blue cabs in the city. This is something that we have called P of B in the earlier description of this problem. Now, suppose we have a witness, and let W be the event where the witness says that the involved cab was a blue cab. In this setting, W complement is going to correspond to the event that the witness says that the involved cab was a green cab. We have the following tree diagram where the first layer corresponds to the color of the cab, and the second layer corresponds to the witness testimony given the color of the cab. So we have four different conditional probabilities to work with over here. The probability of W given B, that is the probability that the witness says that the involved cab was blue, given that the involved cab is blue. The probability of W given G is going to be the probability that the witness says that the involved cab is blue, given that the involved cab was actually green. The probability of W complement given B is going to be the probability that the witness says that the involved cab is green, given that the involved cab was actually blue. And finally, the probability of W complement given G is going to be the probability that the witness says that the involved cab was green, given that the involved cab is actually green. The events W given B and W complement given G correspond to events where the witness is correct in their testimony, whereas the events W given G and W complement given B correspond to events where the witness is incorrect in their testimony. We now want to ask the following question. What is the probability that the involved cab was a blue cab, given that the witness says it was a blue cab? We are looking for a posterior probability given by the formula probability of the event B happening, given that W has happened. There is a typo over here. It should have been a W instead of a in the video. So we'd like to use Bayes' theorem to get the following formula. The probability of B given W is going to be the probability of W given B times the probability of B divided by the probability of W given B times the probability of B plus the probability of W given G times the probability of G. We now use the full power of Bayes' theorem by making prior assumptions on the ability of the witness to make correct observations. So this is going to be quantified by choosing a number P that is going to lie between 0 and 1, and it is going to correspond to the probability that the witness makes a correct observation. Notice that the events W given B and W complement given G correspond to situations where the witness has made correct observations, right? And as a result, the probability of W given B and the probability of W complement given G will both equal P. Similarly, the events W given G and W complement given B correspond to situations when the witness has made incorrect observations. And as a result, the probability of W given G and the probability of W complement given B is going to equal 1 minus P. Let P of B be the proportion of blue cabs in the city. And we already described that this is going to be the probability that the involved cab is a blue cab under no additional information from the witness. We'll call this number Q, which is going to lie between 0 and 1. So our updated tree diagram looks something like this, with the first stage corresponding to the color of the cab and the second stage corresponding to the witness testimony. And our updated probability equation for the probability of B given W comes out to be this nice symmetric equation given by P times Q divided by P times Q plus 1 minus P times 1 minus Q. This is a beautiful equation which is going to lead to three important cases depending on our prior assumptions on witness reliability. That is our choice of P. And this will illustrate how prior subjective choices affect posterior probabilities. The first case is when the probability of B given W equals 0. This is to say that the witness testimony actually exonerates the blue cab. Probability of B given W equals 0 will imply PQ divided by PQ plus 1 minus P times 1 minus Q equals 0, which is going to imply that PQ equals 0, and this results in P equals 0, which would mean that the witness reliability is 0, which could be the case for a variety of reasons. For example, maybe we know with prior knowledge that the witness is blind, or that the witness was never at the accident site, right? So our prior subjective information is affecting our posterior conclusion of the car being blue given the witness testimony. Also, if Q equals 0, we are dealing with a situation that there are no blue cars in the city, which should mean that the probability that the involved cab was a blue cab given witness testimony has to actually equal 0. The second interesting case is when the probability of the involved cab being a blue cab given witness testimony equals 1. This is to say that the witness testimony results in the blue cab being involved with complete confidence. Solving this equation, we notice that we should have PQ divided by PQ plus 1 minus P times 1 minus Q equals 1, which is going to imply that 1 minus P times 1 minus Q equals 0. This results in the conclusion that either 1 minus P equals 0 or 1 minus Q equals 0. If 1 minus P equals 0, we get P equals 1, which means that witness is completely reliable. In this case, if the witness says that the involved cab is blue, it has to be a blue cab that has been involved in the accident. On the other hand, if Q equals 1, we notice that we only have blue cabs in the city, which means that the probability of the involved cab being blue is going to be 1, irrespective of what the witness says. Finally, we work with the case where B and W are independent events. That is, the witness testimony does not change our perception of whether the blue cab was the involved cab. In this scenario, we should have that the probability of B given W equals probability of B. That is going to imply PQ divided by PQ plus 1 minus P times 1 minus Q equals Q. We will need the assumption that Q not equal to 0 to get Q off from both sides of the equation. And then we will need an additional assumption that Q not equal to 1 to cancel out 1 minus Q from both sides of the equation to get the value of our P to be equal to half. Therefore, we now have that the probability of B given W equals probability of B. That is, that the witness testimony being independent of the blue car being at fault corresponds to setting the prior witness reliability to the probability of a fair coin toss. That is, we are setting P to be equal to half. This lines up with our intuition that if we were to treat the witness testimony to be equally true or equally false, it should not affect our perception of the blue cab being at fault beyond knowing the proportion of number of blue cabs in the city. To summarize, we worked out some basics about conditional probability, described the law of total probability, stated Bayes' theorem, and finally worked out a very detailed example. This is all I want to say for now. Take care of yourselves, and I will see you around.